Welcome to the deep dive. Today we're getting into the SKALE Network, specifically looking at its consensus mechanism.
Yeah, the real engine room.
Yeah.
How all these different computers agree on, the state of the blockchain.
Exactly. How they agree on the transaction order, build that reliable chain, even when, well, things get messy or nodes aren't playing nice.
And we're working from this deep dive document you shared, trying to pull out the key bits.
Right. The goal is to understand how SKALE keeps the chain moving forward. That's liveliness, right? And how it makes sure everyone sees the same history consistency.
Even with nodes crashing or actively trying to mess things up. That's the tricky part.
So let's start there. That basic problem.
Yeah.
Distributed consensus. How do you get a bunch of independent machines, maybe some adversarial ones, to agree on the next block?
It's a classic computer science puzzle. You have your honest nodes just trying to follow the protocol.
And then the Byzantine ones.
Right, the unpredictable ones.
Yeah.
They might send conflicting info, try to stop the whole process, or even, try to create splits in the chain.
They're aiming to break either liveliness, stop the chain, or consistency, create forks.
Precisely.
And the source material hits us right away with this core requirement. The number of Byzantine nodes, CU, has to follow $3 plus 1 WANA and being the total nodes.
Yeah.
Why is that specific number so critical?
Well, it's not just SKALE picking a number. It's like a fundamental limit for secure agreement in asynchronous networks like the internet, where message delivery isn't guaranteed to be instant.
Ah, okay. So it's a proven mathematical thing.
Exactly. Research showed decades ago you absolutely need more than 2/3 of your nodes to be honest and participating to guarantee both security and progress in these conditions. It's the bedrock.
Okay, so operating within that limit, how do the nodes actually talk to each other reliably? Messages get lost online all the time.
They use a pretty robust system described in the source. Reliable delivery with retransmissions. If a node doesn't get confirmation a message arrived, it just keeps sending it.
Okay, makes sense.
And a neat detail is that each node keeps separate outgoing message queues for every other node. And these are handled by separate threads.
So if one node goes offline for a bit, it doesn't block messages to everyone else.
Exactly. Its queue might back up, but messages to healthy nodes keep flowing. The source mentions about a 1-hour lifetime for messages in those queues by default.
So temporary hiccups are tolerated. And what about memory? Nodes need to remember where they are in the process.
Oh, absolutely crucial. The consensus state, proposed blocks, who voted for what, protocol variables, it's all stored in non-volatile memory.
Meaning it survives a reboot.
Yes. If a node just restarts, it picks up right where it left off, more or less. It doesn't lose its place in the consensus stance.
Which brings us to failures. The source differentiates between types of failures.
Right. A simple reboot, like we just said, preserves state. It might cause a temporary slowdown for that node, but the system keeps going. A hard crash is worse.
State loss involved there.
Yeah, state loss, maybe a bad bug, hardware failure, or just being offline for so long that those message queues overflow and critical info is lost.
And the impact. It depends on how many nodes have a hard crash.
Precisely. They talk about a limited hard crash. This is where the total number of crash nodes plus the assumed Byzantine nodes is still within that tolerance limit. So crashed plus Byzantine ballers.
And in that case,
The healthy majority just keeps going. They continue consensus, produce blocks. The crash node, when it comes back, has to use a catch-up procedure to get back in sync. Liveliness isn't lost for the network.
okay, but then there's the widespread crash. Sounds less good.
Yeah, that's when the number of crash plus Byzantine nodes goes over T. So crashed plus Byzantine dollars.
And what happens then? Consensus stops.
It can, yes, liveliness can be lost. Imagine, say, more than 1/3 of the nodes just lose power at the same time, or a major software bug hits a huge chunk of them.
So the chain just freezes. That feels like a big problem.
Liveliness is compromised, yeah. But, and this is critical, the source stresses that security is preserved.
How? If the network is stalled.
Because adding any new block requires that supermajority threshold signature. If you don't have enough active, honest nodes online, more than 23 of the total N, you simply cannot gather enough signature shares to create a valid signature for a new block.
Ah, I see. So no new blocks can be added, which means no incorrect or conflicting blocks can be added either. It fails safe.
Exactly. It prevents forks, which is the key security property. It prioritizes consistency over liveliness in these extreme failure scenarios.
Okay, that makes sense. So if it does stall like that, how does it get going again?
There's a specific catastrophic failure resolution protocol. Nodes detect the long stall. And interestingly, they use the Ethereum mainnet to coordinate the recovery.
Really? They fall back to Ethereum.
Yeah, as a coordination layer. To agree on a consistent state to restart from, maybe decide on who participates going forward, and synchronize a restart time after some mandatory quiet period.
Clever. Using a known, secure base layer for emergencies. Okay, let's shift from failures to how the chain actually gets built block by block. What's the basic structure?
Pretty standard blockchain structure. A sequence of committed blocks, B0, B1, B2, up to the tip. Everyone starts with the same genesis block, block 0, all stored persistently, of course.
And the key properties, again, are liveliness and consistency.
Right, liveliness meaning it keeps growing. The source mentions even empty beacon blocks get added every 3 seconds or so if there are no transactions, just to keep things moving.
Prevents stalling in quiet periods.
And fork-free consistency, which means block 5, say, is absolutely identical on every single honest node that has it.
And that consistency comes from the threshold signatures we mentioned.
Directly. You need that supermajority sign-off for a block to be considered committed at a certain height. You just can't get that signature for 2 different blocks at the same height if the honesty assumption holds.
Okay, so walk me through one round. How does block I plus 1 get decided?
It's one consensus round per block ID. Basically, every participating node puts forward a proposal for the next block.
Every single node proposes.
Every participating validator node, yes. Then the consensus protocol runs, evaluates all these proposals, and ideally picks one winner.
Yeah.
That becomes the next block.
And if no single winner emerges?
If, for some reason, no proposal gets enough support or there's ambiguity, an empty block gets committed instead. Liveliness maintained.
How does a node decide what transactions to put in its proposal?
It looks at its local queue of pending transactions from users. If everything fits under the max block size, looks like 8 millib, it takes them all.
And if there are too many?
It takes the oldest ones first, up to that 8 millib limit. And within the block, the transactions are ordered deterministically based on their hash. Keeps it consistent.
Any empty proposals?
Yeah, if the node's transaction queue is empty for that beacon time, about 3 seconds, it just proposes an empty block.
Now, the source mentions something interesting. Transactions aren't removed from the queue when proposed. Why?
Yeah, that's important. They stay in the proposing node's pending queue until the block containing them is actually committed to the chain.
Because the node doesn't know if its proposal will win yet.
Exactly. It might need to include those same transactions in a proposal for the next block if its current proposal doesn't make it.
Okay, this feels like where the real magic needs to happen. How do you ensure everyone gets the data for the winning block and everyone agrees which block actually won?
Right, it's a 2-stage thing, really. First is making sure the data is available. They use something called the block proposal reliable communication algorithm. Think of it as a data availability protocol.
How does that work?
When a node, say Alice, proposes a block, she sends it to her peers. Bob receives it, stores it, and sends Alice back a threshold signature share, confirming he has that specific proposal.
Okay.
Alice collects these shares. Once she has shares from a supermajority of nodes, she combines them into a single threshold signature for her proposal. Let's call it S. Then she broadcasts S to everyone.
So S is proof that a supermajority has the data.
Precisely. And the rule is, honest nodes will only participate in the next phase, the actual agreement voting, for proposals where they've received and verified this S signature.
Why is proving a supermajority has it so key?
Because it guarantees that if Alice's proposal eventually wins the consensus vote, any other honest node, maybe Charlie, who didn't get the full data initially, knows he can reliably get it. He knows the data exists and is stored by a majority of honest nodes because S proves it. Data availability is guaranteed before the final agreement.
Got it. S ensures the data is findable if it wins. So how do they agree on the winner?
That's the second mechanism. The core agreement protocol. They use a pluggable component called asynchronous binary Byzantine agreement, or ABBA.
Binary.
Meaning yes, no. Yes. It's designed for asynchronous networks, tolerates fewer than 13 Byzantine nodes, and the outcome for each instance is just yes or no.
Crucially.
It guarantees that all honest nodes decide on the same binary value.
And it has that common coin thing you mentioned.
Yes, it also outputs a pseudo-random number, the common coin, which is useful later.
So how does this binary yes-no thing work when you have n different proposals?
For each block round, they run n instances of ABBA in parallel. One ABBA instance for each node's proposal.
Okay. So ABA instance 1 decides yes-no for node 1's proposal, instance 2 for node 2's, and so on.
Exactly. At the end, every honest node has a vector, a list of n yes-no results, one result for every proposal.
And from that list of yes-no votes, How do they pick the single winner?
It's deterministic. If only one proposal got a yes from its ABBA instance, that's the winner. Simple.
What if multiple proposals get a yes?
That's where the common coin comes in. They use a value derived from the common coins of all the ABBA instances to pseudo-randomly but deterministically select one winner from the set of proposals that got a yes.
Deterministic is key, so everyone picks the same one.
Absolutely. And if, in some unlikely case, all proposals get a no vote from their ABBA instances.
Empty block.
Empty block, exactly. This whole process guarantees liveliness. You always get a block.
Yeah.
And consistency, everyone agrees on the same block or the empty one.
Makes sense. When do nodes actually cast their votes in these NABBA instances? What's the trigger?
A node only votes in the ABBA instances after it meets two conditions. One, it has received the data availability signature S for a supermajority of other nodes' proposals.
Okay.
And two, it has successfully sent its own proposal, along with its S signature, to a supermajority of its peers. Once both are true, it casts its votes in the ABBA instances.
How does that end up looking in terms of votes?
Well, an honest node following this will likely vote yes for the proposals it received properly with an S, roughly 2 and 3 plus 1 proposals, and no for the others it didn't get an S for in time.
Okay, so ABBA runs, the common coin picks a winner if needed. What's the final step? Putting it on the chain?
Finalizing, yeah. The node identifies the winning proposal ID. It checks if it has the full data locally. If not,
it downloads it using that guarantee from the S signature.
Right. And the source mentions an optimization, splitting the proposal into N1 chunks and downloading different chunks from different peers in parallel. Faster, less load on any one peer. Once it has the full winning proposal data, it verifies the final supermajority threshold signature specifically for that winning block. Remember, S was just for data availability before the vote. This is the final seal of approval.
Right.
Then it commits the block and that final signature to its local storage. The chain grows by 1.
What about those nodes that had a hard crash and are coming back online needing to sync up?
They have a separate background process, the catch-up agent. It's always running, talking to peers, downloading blocks the node is missing.
Does it verify signatures too?
Oh, yes. It only accepts blocks that have that valid supermajority threshold signature. So it reconstructs the verified chain state. The source notes a node can start participating in consensus for new blocks fairly quickly after restarting, but it won't propose its own blocks until catch-up is complete.
Makes sense. It needs the full history to build valid proposals. How about storage? Does it just grow forever?
There are limits. The source mentions a rough allocation, 33% for the blockchain blocks themselves, 33% for the EVM state.
The smart contract data and account balances.
Exactly. And 33% for everything else, like consensus messages, system stuff. If the blockchain part gets full, it starts pruning the oldest blocks in chunks of 1024.
And the EVM state.
If that fills up, transactions that need to write new state will just fail. You'd get an out-of-storage error, like on Ethereum sometimes. And if the consensus message storage fills, it drops old messages, which could, impact performance temporarily.
Okay, let's shift to the user side. EVM compatibility is mentioned as a goal.
Yeah, high compatibility. They want tools like MetaMask, Truffle, Web3.js to just work. They run the standard Ethereum virtual machine, unmodified.
Executing transactions from the committed blocks in order.
Right, and using LevelDB, apparently, as the database for the EVM state storage.
Now here's a biggie from the source. No gas fees for users on Scale chains. That's different. How do they stop spam or denial of service?
That is a major design choice, yeah. Instead of paying gas fees in tokens, the user's client has to perform proof of work.
Like Bitcoin mining, but on the user's machine.
Sort of, but much smaller scale. The amount of computational work required is proportional to the gas the transaction would have cost on Ethereum. PoW will use K gas limit, basically.
So the user pays with CPU cycles instead of tokens.
Exactly. If a transaction arrives at a node without proof of sufficient client-side work, the node just rejects it. DOS prevention via computation.
And that constant K can be tuned.
The source says K is being researched, possibly for dynamic adjustment based on how busy the network is. That's interesting.
Very. So how do users actually connect? What tools work?
Right now, it's the standard JSON RPC API. That's what things like MetaMask use to talk to Ethereum nodes, so it provides that compatibility.
But the source flags a future consideration for reads.
Yeah, this is important for security. Right now, if you ask a single node, what's my balance? Using JSON RPC, a malicious node could potentially lie to you.
Because it's just one node answering.
Right. So they're planning for multi-node reads. The client would ask, say, 10 nodes and get back a response signed by a supermajority, proving the answer is consistent across the network.
That extends the consensus security right down to simple balance checks.
Exactly. Hardens that user interaction layer significantly.
Okay, let's wrap up this deep dive. We've definitely gone through the nuts and bolts of scale consensus.
Yeah, we've seen how they tackle that core challenge of agreement in tricky network conditions with potentially bad actors. That $3 plus one a limit is key.
And the tools they use? Reliable messaging, threshold signatures playing double duty for security and data availability.
That ensemble of ABA instances for deterministic agreement, and then the different layers for handling failures, from catch-up to that Ethereum-based catastrophic recovery.
And it's all balanced with this user-facing model trying to eliminate gas fees using client-side POW instead.
It really paints a picture of the complex engineering needed to build one of these decentralized systems that aims to be robust against failures and attacks. Understanding this stuff shows you what's under the hood.
So here's a final thought for you, the listener, to chew on. We saw that even with all these mechanisms, really widespread problems, massive outages, major bugs hitting lots of nodes can still stall the chain because security is prioritized over staying live in those worst-case scenarios.
Right.
So how do these networks manage the tension between needing to constantly innovate and update code, which always risks introducing bugs, and the absolute necessity for stability and resilience? And how might those future plans, like dynamic POW or verifiable multi-node reads, change that balance?
Yeah, that's the ongoing challenge, isn't it? Balancing progress with unwavering stability. Definitely something to think about as you watch this space evolve.